Hello students. Then we'll take the discuss about here the condenser topic and condenser topic in the vapor power cycle, and they discuss the one numerical belongs to the condenser. The mass of cooling water required in a condenser. That means whenever you taken the any numerical of condenser, that time the cooling water is required. That means how much amount of mass of cooling water is required in condenser so that the steam can be condensate can convert to the excited liquid. The first one we discuss about the some theoretical part of the mass of cooling water in the condenser and discuss the one numerical. In a jet condenser, the exhaust steam and cold water mix directly, so the resulting temperature, the condensed steam and water is the same at its outlet. But in surface condenser, temperature of condensate and temperature of water may differ. Listen, in this case, what happens in jet condenser, exhaust steam and cold water mix directly. In jet condenser, what happens in this case, the cold water and exhaust stream from the turbine mix directly, and so the resulting temperature of condensate steam and water is the same at outlet. But in surface condenser, the condition is different. In jet condenser, direct contact of its exhaust stream in cold water. But in case of surface condenser, temperature of condensate and circulating water differ. Then we derive the equations. What are the derivations for that one? First of all, you have to consider quantity of circulating water M. Then ms quantity of steam condensed. This is the ms. The temperature of wet steam temperature of the wet exhaust steam is the T, capital T. Then Tc, temperature of condensate degree Celsius. Temperature of wet exhaust steam is T, and temperature of condensate is Tc. That is the C indicate the condensate, and the sensible heat or enthalpy of water at temperature degree Celsius, sensible heat or enthalpy of water is considered HFG. HF is nothing but the sensible heat. HF means sensible heat, or you can say that the enthalpy of water. HF means sensible heat. HFG means latent heat, that is the enthalpy of evaporation of steam at temperature degree Celsius. HFG means latent heat of enthalpy. HF means sensible heat. Then X means Dyna's fraction of exhaust steam because the steam taken from the turbine. Therefore, Dyna's fraction of steam. T1 is the inlet temperature of cooling water, and T2 is the outlet temperature of cooling water. Then S suffix C, sensible heat or enthalpy of condensate. Sensible heat or enthalpy of condensate. And CW means specific heat of water. You also have 4.2 kilowatt, Kelvin. That means CW is the specific heat of cooling water. The first one, you have to condenser section. What happens? The heat given by the steam equal to the heat absorbed by the cooling water. Suppose consider turbine. You are getting a steam from the turbine and enter into the condenser section. What happens? The steam is entered into the condenser. That time in condenser the flowing water, cooling water flowing, and the steam is entered into the condenser. The steam, that is steam, have energy. The heat rejected by steam equal to heat gained by the water is occur in the condenser section. Therefore, you can do write the equation: heat given by the steam, the heat rejected by the steam equal to heat absorbed by the cooling water. For you have to consider surface condenser. What happens in surface condenser? You write down the mass of steam into HF plus HFG minus SC. This equation what indicates the mass of steam into HF. HF means nothing but the sensible heat plus X HFG. HFG means latent heat of enthalpy and minus SC. Now sensible heat of condensate, that is sensible heat of water minus sensible heat of condensate, equal to CPW, that means the specific cooling water, specific heat of cooling water. Mass means the mass quantity of cooling water in this case into T2 minus T1, that difference by the in the cooling water. Then for solving this equation, we are getting the mass m equal to ms into in bracket hf plus xhfg minus sc divided by cpw, that means the specific heat of cooling water in bracket temperature difference at T2 minus T1. This equation used for surface condenser. Then for jet condenser, we already discussed, given in the case what is happening, the directly contact with the exhaust stream with the cold water. Therefore, the resulting temperature of condensed steam and water is same at the outlet. That is T2 equal to Tc. Therefore, M equal to Ms into HF plus XFG minus SC, Cp equal to Tc minus T1. In this case, what are the difference between them? What is in this case difference? Difference is only that the HF X HF HSC T2 minus T1, the Tc minus T1 in this case. This is difference Tc minus T, that the condensate, that is the condensate temperature, Tc temperature of condensate minus T1 in this case, and T2 are the temperature difference in the cooling water. And you are getting the equation from the mass of cooling water required condenser for different condenser. For the surface condenser formula is different and jet condenser formula is different, only the temperature difference. Then we discuss to take the one numerical based on that one. The first one we will take the one numerical. Uh, a 175 kilowatt steam engine consumes 9 kg of steam per kilowatt. The back pressure of the engine and the condenser pressure are equal to 0.15 bar. Temperature of the cooling water at the inlet and the outlet are 15 degrees Celsius and 28 degrees Celsius respectively. The temperature of the condensate is 29 degrees Celsius. Determine the quantity of cooling water required per hour if the steam exhausted to the condenser is dry saturated. The first of all, you have to identify the numerical belong to which cycle. So in this case, the condenser is given, that means the numerical condenser. Then first of all, the steam engine consumes 175 kilowatt. The power output is given in this case 9 kg of steam per hour. That the 9 kg of steam is circulating the cycle. The back pressure of engine and condenser pressure. The condenser pressure is given 0.15 bar. Temperature of cooling water at inlet and outlet is given. Both temperature of cooling water is given. Temperature of condensate is also given. Tc is given. Determine the quantity of cooling water. That means you have to mass of water. You have to find out the total mass of water. How much amount of quantity of cooling water required per hour if the steam is exhausted to the condenser is dry saturated. In this case, what happens, the condenser, whenever the steam enter into the condenser, that time the steam is dry saturated. So you have to find out the total steam used per hour. That the mass of steam. That the mass of cooling water also find out, and the mass of total steam per hour is required. First of all, to solve this numerical, it requires the steam table. Go to the steam table. From steam table, table A 1.2, and you have to go through the pressure line 0.15 bar. At 0.15 bar, you have to find the value of enthalpy, entropy, sensible heat, latent heat. There's HF. You have to find 225.91 kg per kg. Then HG 2599.1 kg per kg. Then HFG 2599 minus 0.1 minus 225.91, 2373.19 kg per kg. You are getting HFG. You are getting the values latent heat, sensible heat. Then find out the cooling water per kg of steam. Put this formula for this one, because this numerical belongs to which one? Belongs to the surface condenser. Therefore, you have to put this formula SF HF plus from HF plus XFG minus SC Cp T2 minus T1. That you have to put the values. You will get the M equal to 45.61 kg per hour per kg of steam. And then in this case, what is given? The data is given. The data in the given numerical CPW is not given. You have taken CPW, that is the CPW is nothing but the specific heat of cooling water. You have taken 4.186. Here you can take the 4.2. Then you are getting the mass of cooling, mass of water 45.61 kg per hour per kg of steam. This total steam used per hour. That is, in this case, 9 kg of steam is circulating in the cycle. That you have to multiply this equation, multiply that one. 175 is power is given. You will get 1575 kg, 1575 kg. Then you have to find total circulating water used per hour. That this is the total steam multiplied by 45.61 the cooling water of steam. You will get 71 835.75 kg, and this is the total circulating water used in this equation. That means in this equation what is given in this case? In this case, you have to discuss how much amount of cooling water is required in condenser to condense it, and you have to find out how much amount of steam is calculated, how much amount of cooling water is get. This is the end of the today's session.